this video, we're going to look at a different kind of manufacturing process. Instead of removing or reshaping material, we're going to be building it up layer by layer. This is called additive manufacturing, also known as rapid prototyping or, more commonly, 3D printing. Additive manufacturing is the process of making a physical object from a 3D digital model, typically by laying down many thin layers of material in succession. This contrasts more traditional processes like machining, forming, extrusion, and casting, where material is either reshaped or removed in order to achieve the final product. But how exactly do we build up these layers to form a part? There are a variety of processes which can be used to bridge the gap between the 3D model and the final printed part. They can be roughly grouped into 7 categories: direct energy deposition, inkjet, lamination, material extrusion, photopolymerization, powder bed fusion, and powder deposition. But for now, we're going to just look at material extrusion and powder bed fusion processes, since these are the more commonly used techniques in the aerospace industry. Here, the print material is initially in the form of a filament wire or pellets, which are heated up and extruded through a nozzle onto a build platform. Starting at the base of the part, layers are built up sequentially. This is called fused deposition modeling or fused filament fabrication. Depending on the type of printer, parts can be made from either polymers or ceramics. Extrusion processes can also be used with composite materials. FDM, for instance, can be used to create parts with short chopped fibers floating in a polymer matrix. We can also use extrusion processes to create composites with continuous fibers in a process known as continuous filament fabrication. The process is the same as FDM, but can be implemented in 2 different ways. Either a continuous strand of fiber material is fed into the same nozzle as the polymer matrix material and extruded, or a second nozzle is used to feed the fiber onto the build platform and fuse the fiber and polymer matrix material together. Both of these have the advantage of creating high-strength, high-stiffness structures because the fibers are continuous. The second type of process works by fusing material together. Here, the print material starts as a powder, which is pushed by a roller to cover the build platform. A laser then heats up the powder to fuse it together into a cohesive layer. Then the build platform moves downwards, and more powder is added for the next layer. A major advantage of this process is that it can be used with a wide variety of materials, such as metals, polymers, ceramics, and glass. For metals, the process is called selective laser melting, and for other materials, it is called selective laser sintering. The concept is the same for both. The only difference is that metals are melted by the laser, as the name suggests, while other materials are sintered, meaning they are heated to the point where they fuse together, but are not yet completely liquid. But regardless of the process, additive manufacturing has several advantages over more traditional manufacturing methods. For instance, it can be used with a wide range of materials, as we saw earlier. It also allows for greater flexibility in part shape. Intricate features or complex geometries that would be difficult to cast or machine accurately are easier to produce when built up layer by layer. This flexibility also means that a single printer can produce a virtually infinite number of parts and designs, as opposed to a process like casting where a unique mold has to be created for every individual design. Additive manufacturing can also greatly reduce production time. Designs that could take even a highly skilled technician a few days to produce can now be printed in a matter of hours. It can also be considered more sustainable, since little to no material is wasted in the production process. But, as with any manufacturing process, there are disadvantages that an aerospace structures and materials engineer should keep in mind. For instance, the startup costs of additive manufacturing can be prohibitive since it is still relatively new. Similarly, switching to additive manufacturing requires all new machinery and tooling, which is costly. Certification is also still an issue. Because additive manufacturing is so new, it will take some time to establish whether these various 3D printing techniques are safe to use for different types of aircraft structures. And depending on the process, parts may have some anisotropy due to the way that layers are built up. Though this isn't strictly a negative quality or disadvantage. It does, however, need to be considered when designing a component. So, when are we getting a 3D printed plane? Well, it might still be a little while, but that doesn't mean that additive manufacturing isn't being used in other ways in the aerospace industry today. For example, several of GE's new aircraft engines contain various 3D printed components, including the low-pressure turbine blades and fuel nozzle tip, which greatly reduces the complexity of the engine and increases maintainability. On the ground, KLM Engineering and Maintenance uses additive manufacturing to save time during maintenance and repairs. For instance, 3D printed covers have replaced disposable tape which protect engine turbine blades during maintenance. And if, say, a cabin component breaks early and needs to be repaired, a replacement part can be quickly printed in-house and installed, instead of having to wait for the manufacturer to produce the part and send it to the maintenance facility, which could take some time.
3D printing has also helped us safely get to space. In 2020, SpaceX launched its first crewed mission with the Crew Dragon capsule. The capsule is equipped with a launch escape system comprised of 8 Super Draco engines, which have a primarily 3D printed internal structure.
The structural complexity of rocket engines means that normally hundreds, if not thousands, of individual parts need to be joined together, thereby increasing production time and structural weight. By using additive manufacturing techniques, however, entire, highly intricate structures can be built in one piece, saving weight, time, and money.